Clinical Service for Inherited Retinal Dystrophies at the University of California, Davis. Dr. Sieving earned his bachelor's degree in physics and history from Valparaiso University, followed by a master's in nuclear physics at Yale University, where he also attended law school. Dr. Sieving studied medicine at the University of Illinois, where he later obtained his PhD in biomedical engineering, followed by a residency in ophthalmology. He conducted a postdoc focusing on physiology at the University of California, San Francisco, under the mentorship of Roy Steinberg, and undertook his clinical fellowship in genetic retinal degenerations under the guidance of Elliot Bernson at Harvard Medical School, Massachusetts Eye and Ear Infirmary. Dr. Sieving is internationally recognized for his research in electroretinography to understand the mechanisms of dysfunction in retinal degeneration, as well as genetic, cell biologic, and translational studies of inherited retinal diseases. Notably, his lab was the first to initiate an in vivo human gene therapy clinical trial at the National Institutes of Health for any disease, which focused on X-linked retinoschisis using AAV vectors, laying critical groundwork for translational gene therapy approaches in ophthalmology. His group also conducted the first human clinical neuroprotection trial using CNTF as a rescue for retinitis pigmentosa. Dr. Sieving served as the director of the National Eye Institute from 2001 to 2019. Under his leadership, the NEI launched the Audacious Goals Initiative in regenerative medicine. Dr. Sieving is an elected member of the American Ophthalmological Society, Academia Ophthalmologica Internationalis, the US National Academy of Medicine, and the German National Academy of Science. Is the recipient of numerous awards for his scientific leadership, has published extensively in top-tier journals with over 250 scientific papers and book chapters, continues to advise on scientific policy, translational research, and emerging therapies in ophthalmology. His research bridges the gap between bench science and patient care. Please join me in welcoming a visionary leader in medical science and a tireless advocate for those affected by retinal diseases, Dr. Sieving.
Thank you for that marvelous introduction. And I should say hi, Subair, and hi, Tony, and a few people on Zoom. And thank you, everyone, for attending. I am going to be talking about photoreceptors. This is a kind of difficult place to talk about photoreceptors and rhodopsin and things such, because this really is the epicenter of work on photoreceptors, both the basic study of them and translating ideas into potential therapies. But my excuse is I'm a clinician, and I have been interested in how people see. I got interested in photoreceptors from the concepts of physics, because photoreceptors sit in the dark for days and days, and in total darkness, nothing much happens. And then a photon comes and turns one of them on, or many of them on, and we see each other. And that has been, for me, a fascinating driver to understand clinically how one thinks about photoreceptors. A couple of facts that all of you are very familiar with. We've got a lot of them in the retina. 120 million rods, plus minus a few, 6 million cones that see color. Each of those rods is organized to respond to a photon. They're single photon detectors. They saturate in daylight, so they turn off, which means if you're an achromat, you're really disadvantaged, and so you wear very dark sunglasses. The retina is organized to optimize processing that signal, because signals from perhaps 300 rod photoreceptors ultimately converge onto ganglion cells. That's an idea that will come up a little later. Rhodopsin. I think this is not the audience to be talking about rhodopsin to, but the last 2 points are worth thinking about. Rhodopsin is an incredibly stable molecule You put it on the shelf and it takes 350 years, plus or minus a few, to activate. And that spontaneous rate of activation is very slow, which is critical because we have so many of those rod photoreceptors. And as stable as rhodopsin is, it means that every few minutes, there is a spontaneous activation in a rod, and then it's the upstream signal processing that has to deal with that. I'll return to that spontaneous idea in a moment. Now, one of the things that caught my attention as a medical student was the concept that mutations in this rhodopsin gene are not very good for the health and survival of the retina. Here is the quintessential retinitis pigmentosa picture with a lot of pigment that's accumulated, pouring out of the retinal pigment epithelium and accumulating in the retina, giving it the intraretinal bone spicule, because that's what it looks like, something histology. And it relatively spares the center of vision, the macula. So the talk is going to focus on what's happening with rhodopsin and what is happening to the photoreceptors. I'm breaking the talk into these 5 components, so if one bores you, I hope the next one catches your attention. We're going to start with rhodopsin signaling using a measure that probably you don't know about, the early receptor potential. The early receptor potential, Richard Cohn in 1964 stuck an electrode in the retina by the photoreceptors, flashed an intense flash of light, and saw a response that was extraordinarily fast. And what's happening on the bottom left, rhodopsin catching light, the retinoid changes configuration. It shoves the molecular structure of rhodopsin around. That molecular structure, rhodopsin sitting in a membrane, so charge and membrane capacitance gives you a very fast photovoltage. Now, of interest, Elliot Burson, who was one of the real founders of retinal degenerations, in 1970 took interest and recorded the ERP and found that it recovered faster than normal after bleaching. And similarly, for the women who carry the trait of X-linked RP, it was also faster. I'm going to get around to that in a moment, but that was one of the drivers. The ERP is somewhat difficult to record because you usually use a metal wire electrode touching the cornea to record the electroretinogram. But with an intense flash of light, you get a photovoltaic artifact that just obscures things. Look at the speed of this. 1 millisecond on the bottom. That first R1 going positive, the R2 going negative, the swing there is about 100 to 200 microvolts. And the latency is extraordinarily fast, as Cohn had said in 64. And at the bottom with end stage RP, there's no signal. There's no rhodopsin, no signal. Well, let's look at a clinical case. So I had developed this tool. I was interested in it. And a 38-year-old guy comes into the eye emergency room, and he'd been hammering away at a piece of metal, and he caught a sliver of metal that penetrated his cornea and settled in the retina. Now, metal, iron toxicity is called siderosis. And the question is, do you go in and remove that? Quite frankly, today in 2025, probably vitreoretinal surgeons would just go and remove it. But when this was happening, 1983, retinal surgery was dangerous, and so at first they left it alone. But at 6 months on the bottom, you can see that compared to the unaffected left eye, LE, that response is diminished. And so something needs to happen, and surgery was done. Meanwhile, I had opportunity to record the the ERP from both eyes. You can see it's quite symmetrical. There's nothing happening to the ERP amplitude, despite the fact that the rod photoreceptors are not signaling properly, as seen in the ERG. So conclusion is the ERP is not rod function, something that precedes rod function. And the siderosis affects the photoreceptor signaling, but does not affect the ERP. Here's another interesting case. I think, just boasting a moment, I think I was the first one to see a patient like this. I was a resident, and a young woman walked in and said she'd been having sniffles for a week, and her vision in one eye was not doing so well. The left eye, OS, in the middle figure. And you can look in with fundus fluorescein angiogram and see that there are copious little tiny spots. Recording the ERP on her, the ERP is diminished. And at 68 days, there's a bit of recovery, but not full recovery. Now, I wanted to measure the kinetics of the ERP. And normally one would flash a light or bleach and then watch regeneration happen. In this case, I'm going backward. Is there a pointer on this? Oh, here's a pointer. So flash first time, wait 45 seconds, flash second time, third time, fourth time, and that progressively knocks down this signal, but it recovers a bit in that 45 seconds of darkness until it finally asymptotes. And for normal subjects, the asymptote is here. For her eye, the asymptote is on the bottom. There is a closed form solution to the mathematics of this. And from that, one can extract the amount of rhodopsin that's bleached and the recovery time constant. And in her eye, on the bottom, at days 113 and 68, she is outside. She's recovering slowly. By day, yes, so she's recovering slowly. So the kinetics are retarded. So the finding is that the ERG A wave reduction implicates rod functional impairment, but the ERP indicates that both the cones and the rods are involved. And thinking through the issue, it turns out that the conclusion would be that there is slow cycling of rhodopsin through the RPE, probably due to her infectious condition, which ultimately got the name multiple evanescent white dot syndrome. So back to the question. Person found retinitis pigmentosa. This response recovered too quickly. However, Hyman and Wheel and Harris Rips looked with other techniques and disavowed that, said the recovery kinetics were normal. So what we did is to look at a series of RP patients, and in fact, we did find that the recovery was a little bit faster. But here's the trick. This is not a matter of pigment speeding up, which doesn't make sense for a sync photoreceptor. Instead, the ERP is a mixture of rods and cones behave more quickly in pigment regeneration. When you kill off the rods by disease, what remains is a little bit faster, as Burson had found. So at the bottom, would we repeat this again today? Well, we would do it with a genetically defined population and make some sense out of what's happening. But also the bottom line is there is no evidence that the kinetics of visual pigment regeneration in a sick photoreceptor from retinitis pigmentosa, there's no evidence that that is speeded up. Let's move one step further then. Well, just to summarize, the ERP then is actually rhodopsin sitting in the rod membrane, catching light, configuration changes, charge is produced, and you can record it at the cornea. So it's a rhodopsin signal. Let's move downstream a bit and look at the ERG. ERG, A waves, photoreceptor, B waves, bipolar cells, used to be thought mutant cells, but probably bipolar cells directly. At the bottom, bright flashes, A wave, B wave, and when you make the flash progressively dimmer, the A wave subsides, the B wave remains, and the B wave then settles into obscurity. And intensity response curves as shown there. So I was curious, what happens if we really look carefully with dim flashes? After all, these rods are responding to individual photons. Well, now the story changes. A wave at the bottom, B wave subsides nicely. But here, there's a scale change from 100 microvolts to 20 microvolts. There is something else that is showing up. The A wave is gone, but there is this threshold response in the dark at scotopic threshold. So when I was with Roy Steinberg, just called it the scotopic threshold response. Roy's lab was doing intraretinal recordings, so I stuck a electrode in the cat retina and recorded beginning at the bottom of the retina and moving to the ganglion cells. And you can see with a very dim flash of light, the activity is not by the rod photoreceptors, it's here in the proximal retina. Or you can plot it out. This is another stimulus, but same thing. Photoreceptors at the back, negative in the proximal retina at the depth of ganglion cells. And that would give a dipole negative at the vitreous in the cornea and give this negative scotopic threshold response. It is spatially tuned. It's simply a mass action. Little tiny spots of light, progressively bigger. And the amplitude of the STR just grows as you give it more photons. So this is a light response and not a tuned inner retinal response. Quick conclusions. The scotopic threshold response STR is the A wave, the first negative response to very dim threshold stimuli, negative at the cornea. This has the characteristics of amacrine cell activity. And then we did some blocking ultimately with GABA and glycine and isolated the amacrine cells and in fact showed that amacrine cells may be the A2 amacrine cells that are principally generating that. Previously I showed you cat, here I'm showing you cat, monkey, and human, and the same phenomena hold true across species. Can you record it this afternoon in the class if you have the time and patience and a good quiet subject? These are simply repetitive stimuli recorded on a oscilloscope screen. We didn't have digitized responses at that point. And you can see that it's very reproducible. Also note something important here. The onset of the light, nothing happens. It sits there for a while and then it goes negative. This is out at 100 milliseconds after the flash. So it cannot be a photoreceptor response. It has to be some processing in the retina. And now recollect what I said at the opening, about 300 rod signals from 300 rods feed ultimately into the ganglion cells. So there is massive gain of neural activity, accounting, as you go into the proximal retina. And that made sense for this STR. Well, let's look at a couple cases. How about ganglion cells? Is this coming from ganglion cells? The answer is no. This is a 22. She was out trick-or-treating when she was 7 or something, and in the night, caught her foot on a crack in the sidewalk, fell over, and severed her optic nerve. And you can see the total cupping here on the LE left eye. Total optic nerve fibers are gone compared to the normal right eye. But the STR, it's still there. This is not a ganglion cell response. And so we took a cat, cut the optic nerve in one eye, waited 21 months. I guess I had time in my hands or something. And looked at the histology, and in the unaffected eye here, the ganglion cells sitting up here, and the retina is thinned, no ganglion cells remaining in that eye in the cat. And yet the normal eye on the left versus the atrophic optic atrophy eye in the cat, the STR is still there. This is not a ganglion cell response. It's an amacrine cell response. Good. Let's talk about another story. I think I'll talk a long time with Vladimir today. And you can tell me what the newest version of G90D activity is. This is one of my favorite papers, Hecht-Schleyer and Perrin, 1942. He dark adapted individuals, shown a very dim flash of light until the subject said yes or no. The psychophysics is best framed in yes, no, bivariate responses. I see it or I don't see it. And they concluded that only a small number of molecular transformations is enough to supply the initial impetus for vision. They tested 7 subjects. That yes, no would be 50-50. So instead they chose 60% correct yes answers as their threshold. They accounted for light that was reflected from the cornea, absorbed by the lens and other media, and said that there's probability of a photon going through the rhodopsin and not doing anything. So there's a quantum catch cross-section. And they concluded that 5 to 14 photons absorbed among hundreds of rods can cause a visual perception. I just find this kind of one of those quintessential papers to know about. Okay, patient walks in, 38 years old. I'm in Ann Arbor, University of Michigan, and he's a robotics engineer, one of the companies, and he says, I've always been night blind. My father's night blind. My son's night blind. That's important because if this is on the X chromosome, never is male to male to male. So this is an autosome. And when you look at his pedigree, as we detailed it, I think I saw 12 members of this family. But when I saw him the first time, oh, you're night blind, you've been that way since birth. I'm going to look in your eye and see that pigment devastation of retinitis pigmentosa. Looks pretty good to me. I don't see any pigment. I was really surprised at that. And his retinal vessels have normal size. In retinitis pigmentosa, when the rods die, there's retinal pathology. You don't need as much oxygen. And so the vessels auto-constrict. Well, he doesn't have that either. So this is a puzzle. We recorded the ERG in him and a number of others. Whooped his visual fields. Those are normal. These are all affected people. Age 32, I think that's him. His son is up above age 10. There's another panel, but it'd be repetitive going up to age 64. everything looked good for his visual field. He doesn't have any field constriction of RP. Recording an ERG, where in the world did the rod response go? It's gone, not there. And it doesn't matter whether you're 10 years old or 64 years old, it's gone. Meanwhile, look at the cones. They're responding quite respectably. And since the cones are scattered across the retina, when the rod photoreceptors die, cones die also. So this cannot be massive rod death to account for that flat ERG. There was a little bit of pigment to be found in the bottom guy, 64 years old, and you can see that his cone ERG is a bit diminished. Oh, it is diminished. His brother, right here, age 63, brother's doing fine. Looks like that 32-year-old. So this was a clinical phenomenon. Frank Narendorf, who was with me at the time, used did some psychophysics and complicated slide. I won't spend a lot of time on it, but here, this curve, the solid curve, that's what you and I would do. And we would have sensitivity to very dim stimuli, but this guy has sensitivity elevated 3 log units. And his triangles, red triangles, those are his rods. Clearly not normal at low threshold, but they, well, I don't know if they're normal at any point, and we'll get to that in a moment. Meanwhile, the blue cones are acting fine, the red and green cones are acting fine. So this is a rod problem with thresholds elevated 3 log units. And Matt Alpern was at Michigan. He had a densitometer. Frank Narendorf polished the lenses and did some good old-fashioned fundus reflection densitometry. And he found that the rhodopsin kinetics were normal. That pigment was returning back and reconstituting rhodopsin in the normal fashion. Although there was a slight blue shift. So Kefloff, I'll be knocking on your door this afternoon. So rhodopsin is there, normal quantity, thresholds are elevated, 3 log units. What in the world is going on? It's dominant, which means he's got 1 normal rhodopsin gene and 1 abnormal rhodopsin gene to be inherited. So 1 abnormal copy of rhodopsin is enough to destabilize these rods. And thought occurred to me thinking it through, well, that abnormal gene is generating a pigment which isn't stable. And it's signaling the rod photoreceptor that it sees light, even though it's down in a coal mine and there is no light around. That rod is acting as though it's generating its own light. We made a transgenic mouse. Again, put yourself back 25 years. Now you want a transgenic, order it up and you can have it in 2 months. Or is it 3? I don't know. Then this was a big deal. And so we made the transgenic. We also had the rhodopsin knockout. And so we crossbreeded them. We made every combination. But here on top is a mouse with 1 copy of the G90D and 1 copy of wild type. And here's the same genetic configuration. And compared to the hemizygous knockout, it's normal. And this is an old age mouse, 210-day mouse. So this is not killing the photoreceptors. And ultrastructure in a double G90 with no wild type, the structure looks darn good at 36 weeks of age. So this is not killing the rod photoreceptors. No rod degeneration. Rods are normal length, normal ultrastructure. It implies that rhodopsin traffics normally to the ROS because rhodopsin also serves as a structural protein for the rods. So we did some good old-fashioned ERGs. On top, a wild type. On the bottom, added the G90. And on top, the dark is an ERG dark adapted, but when you light adapt, everything speeds up. And the same phenomenon was happening in these G90D mice. Things were acting faster, as though there was background illuminance when there was none. So it was acting as though the rod itself was generating its own light, against which it could respond to photons and give you an ERG. We worked through the kinetics. And the important frame here is on the bottom right. The red is the G90 against a one copy wild type. And there is a sensitivity loss there. And you can do your math up with a statement of 82 photoisomerizations per rod per second, or I think better put, 82 events per rod per second. So it speeds it up, generates the equivalent, what I call dark light. But what's the mechanism for this dark light? This is an interesting mutation because it sits in the opsin pocket right across from the lyse 296, which is the binding for, and it puts a new negative charge there and destabilizes that. And my thought was, simple clinician, it's not holding on to that retinoid appropriately. So it destabilizes the retinal binding, causes spontaneous activation in darkness equivalent to 82 R star per second. Tom Sackmar more or less agreed with that. Gordon Fain, John Lissman had been working on vitamin A deprivation, and they said, well, it's an equivalent light hypothesis. Anoprian says that the G90 partially substitutes for the counter-ion glue 113, opens a pocket, weakly activates transduction in the dark. Everybody's using different terms, but coming to the same conclusion that this involves spontaneous activity in the rod photoreceptor courtesy of this mutant pigment. And now, let's see, what is it from 91 to 20, that's 33 years later, people are still at it. So Vladimir, well, you can tell me your idea. This is last year, King Wai Yao. He said high frequency of unitary electrical events in a rod, each triggered by a single activating complex equivalent to 350 R star per second. And then he says, and the mechanism really isn't understood. So we need an answer eventually. But I'm pleased that our original 82 R star per second and 320 is in the ballpark, at least for physics. We're not chemists. We do powers of 10. King Wai Yao actually extrapolated by a factor of 1,000 because he had a very dilute chromophore. So, turns out this rhodopsin can do bad things to the photoreceptors and kill them. In the first mutation identified, Pro23 hist, or it can give you night blindness from something equivalent to congenital stationary night blindness. I don't like that term, CSNB, congenital stationary night blindness, because I reserve that for the synaptic issues. There are 9 or so proteins in the signaling complex at the synapse. when the rod can't talk to the bipolar cell, well, you're night blind. But this is a very different mechanism, and it's noisy rhodopsin night blindness. Okay, moving on. What happens if you simply remove the ability of the rhodopsin to respond to light? What does that do? There was a student, again, I'm at University of Michigan practicing, seeing RP patients. There's an Usher patient. Usher is vision loss and hearing loss, 3 types of Usher syndrome. She had Usher type 1, which is congenital hearing impairment, rapid vision loss. And she said, my dermatologist wants me to be on Accutane for treatment, but I'm scared about that because my mom checks and says there are some reports of Accutane causing retinal disease. And part of that paper was by Dick Welliver up in Portland. 1996, he had seen a couple of patients who were on Accutane treatment, and they had abnormal dark adaptation curves, abnormal ERGs. Accutane was stopped and things recovered. So this patient was right, and I said, well, we'll monitor you as best we can. Meanwhile, a med student walked in and said, can I have a summer project? I said, hey, you know, that's great. Here, have some rats, give them IP Accutane a couple of weeks, and let's measure the ERG and see what happens. Craig Dolly rats, standard housing, 200 lux. This room, probably about 300 to 350 lux, so standard vivarium lighting. I give retinoic acid, 13 cis, massive dose. This might kill a person, but the rats are okay. Give it for 4 weeks, dark adapt them, and record from them. Doggone it, everything was normal. Responses were normal. There wasn't any pathology going on. And the med student was utterly depressed. He just spent his summer, a failed experiment. So I told him, well, tell you what, walk those animals out in the sunlight. Bright sunny day in Ann Arbor, rare for Ann Arbor, but bright sunny day. And then come back in and record the ERG again. Bingo. No response. It is gone. So we standardized that a little bit more and did a few months of experiments. And here, the untreated control, dark adaptation. Here's the B wave, dim flash because there's no A wave, but these are the rods. B wave, and right after we bleached, light adapted, there's very little response and it grows over 50 minutes. Whereas the Accutane treated animal didn't. And this stuff acts quickly because we treated them 1 hour before bleaching. But if you keep those same animals in normal vivarium lighting and then look at them 6 days later, so these are the same animals, yep, they've recovered normally. So that implies slow rhodopsin regeneration. And so we measured it. And indeed, compared to the controls, this is slow B wave recovery. And it's graded by the quantity of IP injection. But doing that more formally, Ron Bush had done a lot of rhodopsin extraction for his thesis. And so he did it, and wow. Controls, 28-minute 1/E time. The Accutane, 20 hours. Very, very slow regeneration kinetics. Now you got to figure out what's going on. Well, doesn't make sense that the Accutane is actually 13-cis-retinoic acid is in the pocket. That shouldn't be causing this. But can it interfere with chromophore recycling? So Deborah Thompson took a look at RPE retina extract, liquid chromatography, and finds two things. This is normal control on the bottom and Accutane treated animals on the top. Here is the normal in the normal animal, this is, this is 11 cis, not 13 cis, my apologies. 11 cis retinal, it's functioning normally in the control, but it's not showing up in the Accutane treated. And this is the retinol precursor in the pathway of 11 cis. And it is still there. So there is a hang up, the RDH enzyme that is slowing down this regeneration. About that time, I think we published in 2001, about that time, there were beginning to be reports of 13-cis-retinoic acid inhibiting that pathway. And Yamamoto had found that in patients with extremely slow recovery in the dark, called fundus albipunctatus. Fundus means looking at the retina. Albi, white, punctatus, white spots in the retina. You look in, say, oh, I know what that is. That's fundus albipunctatus. Ma'am, how's your night vision? Oh, doc, I can't see anything at night. But if you patch them overnight and then pick them up their house and take them into the lab and record it, ERG is normal in fundus albipunctatus after a long, long overnight dark adaptation. Well, that's curious. And so we got thinking, could this be of any therapeutic benefit? And could Accutane, 13-cis-retinoic acid, be protective of the retina? And in fact, yes, we did the experiments, and it is. These are animals. This is a 48-hour light exposure, 2,000 lux. If this is 300, 2,000 is bright, it damages the photoreceptors. For 48 hours, that's a long time for an animal. And we had given to these animals, we'd given IP Accutane 1 hour before starting that exposure, and we redosed them at 24 hours during the light exposure. Beautiful. The normal control and the Accutane are just lying right on top of one another. But here is DSMO, non-protective, and there's no activity. And looking at histology in these rats, you can see that there is great histology after Accutane protection. So that got us thinking, and in writing the paper, we have a little paragraph right at the end that said maybe this could be helpful for Stargardt, because Stargardt accumulates this byproduct that can't be removed from the retina because ABCA4 is defective. How about if you just slow things down so there isn't as much to remove and not as much to accumulate? Which gets to the idea then that modulating retinoid cycling may be a therapeutic. And this is a program that knows all about that. So nothing from you that is needed on that. Okay. Well, can't forget the cones. They're kind of nice to have. We're looking at each other right now because of the cones. The rods would be saturated in this light. We wouldn't see very much. So for an achromat, you'd be wearing sunglasses indoors. We have 6 million cones, 120 million rods. And RP patients lose their rods first, and their peripheral vision is affected, but the cones predominate in the middle, and until the loss of field gets to be quite severe, they're doing pretty good. So if you could protect those cones, that would be a therapeutic. Well, how many cones would you like to protect? Or if you want to replace them, how many would you like to replace? So how many cones are required to see? Since all this work was done, there's been a revolution in clinical ophthalmology, and that's courtesy of the optical coherence tomography. Look at that pretty clinical retina down here on the bottom. In fact, here are the photoreceptor nuclei. There's some rods and cones. These are all cones here, rod-free zone. And you can see that the outer segment is a bit longer right in the, this is wonderful. But how many of these cones would you really, really, in a pinch, need to save? So let's look at a Stargardt's man. Came to see me last couple of years, 72 years old. He's got 2 mutations. Both of his alleles have mutations. But he is 20/20 and a shade off for each eye. I'd like to just walk through what this OCT is showing us and pictures. Optic nerve head, the vessels look good because his peripheral rods and cones are okay. The pathology for him is limited here, right here, and this is his center of cone density, surrounded by total loss of cones. Total loss of cones. You can appreciate it, but yeah, you can. There are some little spots here where he's losing this center also. But this is where he has 20/20 acuity. Now, when we do the OCT, on the bottom, this is the optic nerve. And here's the fovea center. You can see the thinning of the innermost layers. And he's got a goodly number of cone photoreceptors. And he's got some good structure of the inner and outer segments. Even better for his right eye. Looks semi-normal, but that's adjacent in Stargardt's, totally losing everything. So what this says is, if you can preserve this whole retina, if you can preserve this little tiny center, you can read the road sign, see the lights, traffic lights, and God forbid you can drive okay. Well, the clinical anatomy, recognizing that all of you know this, this is where you have 20/20, the umbo. C is 1.5 millimeters. That's about what he has. How big is that? That's the operational part of looking at these slides. How big is that? Well, if you want to hold out your thumb, the thumb blocks your face. I can see everything around it, but it blocks your face. And that is this area right here. So this is about the width of a thumb held at arm's length. And it has 150,000 cones. But the centermost part, where you have 20/20, has very few, 10,000 cones. If you could save those 10,000 cones, you could actually have 20/20 acuity. Nice image by Helga Kolb. Here is the umbo, and you can see the foveal cones very nicely. So let's protect those. But how many do we need to protect? Well, let's just do a thought experiment, setting it up by looking at what happens if you strip the photoreceptor layer out of the pigment epithelium. This is the pigment epithelium, which is wrapping around the outer segment. And you can see the nice hexagonal array of holes. Now let's take that hexagonal array and again, just for theory, let's make a hexagonal packed matrix. And let's superimpose a Snell and E. The doc says, oh, Ms. Smith, you got 20/20 acuity. You're fine. You're fine. My glasses are working fine for you. That 20/20 E has an arm which occupies two cones side by side. And then there are two that are normally lit and two that are dark, et cetera. And you say, oh, I see an E. Well, it turns out if you remove half of those elements and you kind of squint, you can see that E, it's not an S, not a T, not a 3. You can make out, you can respond, that's an E. That's with 50% of your cones removed. And if you reduce the stringency and say, well, here's a 20/30 letter on the eye chart, boy, it's easy to see, but better if you blur your vision a little bit. So maybe good to have glasses that are blurred. I don't know. All right. So acuity is not highly sensitive to losing lots of cones, at least by this experiment. Another way of testing old-fashioned visual psychophysics, which way do I orient the grating? And there's actually a low vision test, which is grating orientation. How many cones do we need to do that? Well, you can model that very easily. Here's a hexagonal packed cone array. And if we superimpose on that bars that fit on 3 rows photoreceptors, that'd be 20/30 acuity. Oh, and by the way, if you just work backward, if 20/20 is 2 bars, 20/30 is 3 bars, 1 bar is 20/10. And the theoretical limit of acuity that each of us has is about 20/8 or 20/10. Okay, so we tried the experiment. We made this array and we then removed elements. We presented it for just a quarter of a second and said, yes, no, is it right or left? And when you do that, up here on the right side, oh man, you can see that orientation when you've lost 60% of your photoreceptors, at least by this experiment. Not ambiguous at all. And even a 20/30 with 90% elements lost. Andrew Geller did this, and 100% is with all elements. This would be half the elements removed. 90% of the elements, one of the subjects was me, I could still see the orientation. So this is not a great test of visual acuity. Then we tried another experiment. Had it presenting a tiny little spot of light. The tiny spots of light have point spread functions. When you put them in, the optics blur the spot a little bit. So it's not a point of light, it's a distribution of light. The distribution was about 1.25 degrees. And we did it with Stargardt's patients. This is before ABCA4 gene was cloned. And I was going to bet my bottom dollar that the gene for Stargardt's would be in the pigment epithelium. So I was curious last night on the question around the dinner table. Is ABCA4 in the, or was it RP65? Is it in the
ABCA4?
ABCA4? Is it in the RPE principally? Okay. Anyway, we did this experiment, and You can model this with assumptions that the foveal cones are acting independently. That's a pretty good assumption. Multiple photons are required to activate a cone. That's a good assumption too. How many, what do you say? Do you need 4 or 6 simultaneously to activate a cone?
I think it's more than that, probably 100. 100 maybe?
Oh, no, not for a, anyway. I modeled it with 6. Some of the literature said you need 6 photons to be impinge on a single cone photoreceptor in a critical period in order for activation. But these are the assumptions we made. And then you can model it. The probability that you do not see it, and then 1 minus not seeing it equals, yes, I see it. Again, good psychophysics experiment. And you can model this thing and then do curve fitting to your data. Here are the data. 5 Stargardt subjects, and right away you see that they are different from normal. Acuities, 2030 to 2100. But they could see in the center, we checked that. So they did have light perception in the center. They didn't have color problems, which would indicate cone, class of cone problem. And then we gave ourselves 3 models to analyze. First, there were fewer cones. Second, it took more photons to turn a cone on, or it was a combination. Fewer cones and the remaining cones weren't as viable. And what we got was you could lose a lot of cones and the remaining cones weren't in great condition, and yet you could detect them. So according to this, and these are just experiments, theories, 2030 to 2100 acuities in these people, they could be operating with very few cones and remaining cones not in such great shape. Do you believe me? Those are just thought experiments. Let's check some data. Here is a patient with P23 His rhodopsin mutation. She died of lung cancer in the University Hospital, and family agreed to donate her eyes. We had those eyes quickly, processed them well. This field, this is a gold field. We're testing peripheral vision. The red is to see all the way out 90 degrees. And we're limited on the top by our eyelids, et cetera. And here is the nose. The second eye is sitting off on one side. You can't look through your nose, so that's cut off here. That would be you and me. But for her, she's got a little perception just right down the middle. Those cones in the middle are not in great shape. The section missed the foveola. I wish we had that, but this is right next to the foveola. You can tell because it's not fovea because there are inner neurons. But look at the remaining cones. Not very many of them. And the outer segments, here is a normal individual, and here is her. Boy, oh boy. She's got some cones, but those remaining cones are not normal. They are really on their last legs. And if you, instead of looking at the fovea, look in her periphery where she doesn't see things, reason she doesn't see things is she's got no rods and cones. Plus, somebody took an egg beater and just scrambled up the neurons. This retina is in, can you rescue it? I wouldn't count on it. There is just too much pathology going on. So we are going to have to get to these people earlier, which now, courtesy of genetics, we will be able to do. Okay, so to summarize what I showed you, that hexagonal matrix, you can lose 50% of the cones and still figure out what's going on straight ahead. Or if you do the Stargardt spot detection test, you can lose massive amounts and still have 21 acuity. But measuring things in Stargardts, excuse me, the bottom one here, that's the grading orientation, 90%. For the spot detection with Stargardts, it also shows you can have massive loss of cone photoreceptors and still have some retina central function, 2100 acuity. Or in that RP, rhodopsin RPI, you can lose lots and lots of cones and have 2060 acuity. Now, how do you do it? Well, you get Austin Rorda or someone to do adaptive optics and just look at the cones. This was done by Jessica Morgan at Philadelphia. Choroideremia subject, not in the fovea center, but probably valid for the fovea center. 20/20 acuity. This would be a normal eye, and here is the choroideremia eye. And you can see there's loss of cone photoreceptors and everything is slid together to fill in the matrix. And then about that time, Arvo said, note the loss of cones and increased spacing in choroideremia. So there are two observations of this. So the summary here then would be that you don't need all of the cones. Nice to have them. But even if you're successful putting some cones in and having some of those more or less work, you're going to help this person. Conversely, everyone now recognizes that visual acuity is not the way to monitor what's going on. We need other metrics for that. And then one hopes that restoring a few functional cones could be productive and helpful for these people. Last slide. So I've shown you a tour of some clinical observations with photoreceptors. And I think the take home would be that photoreceptors can malfunction in a number of different ways. Acuity, we like it, we want it, but it's fortunately robust even when one has cone central damage. And replenishing a few of those cones would be very useful. Okay, thank you. Appreciate your time. Hope it was entertaining. And thank
you. I'm glad to be next.
Next talk, would like to go back to the noisy rhodopsin. You mentioned that it was because the mutation caused spontaneous activity in the rhodopsin, but it seems like from your graph, it's more than that. It has a signal strength component, so it's dependent on the signal. So I was wondering, what do you think is happening there?
This is there's an overlay of the two things that are going on. One, the visual pigment causes something to happen. The mechanism for that statement is not fully known, but multiple people are converging on the idea that this G90D opsin functions differently, independent of light. It can cause the rod to believe it's in a lit environment. The rod is responding to the intrinsic dark light, noise, or opsin noise, however you want to put it. Then the rod will have its own dynamics, which are designed into the rod to adapt to lighting. And so the amplitudes aren't going to measure up exactly. They're going to be suppressed because you do have the equivalent of external light. This happens to be a very interesting, to me, mutation. As you know, exposing retinas to light, exposing albino rats to light, causes photoreceptors to die. So these retinas are exposed to light. Why aren't the photoreceptors dying? It turns out that this is just the right amount of light to desensitize the rod significantly, 80 to 200, 300 light equivalent events per second. That's a lot. That will desensitize the rods, and it shows up all over, including the person says, I can't see at night. But it's not enough to cause degeneration. The 82 equivalent isomerizations per rod per second is 1/8 of 1 lux. Very dim, but these rods are extraordinarily sensitive to dim light. So it's balanced between dysfunction and degeneration.
Yes, hi, Dr. Sieving. I really absolutely loved your talk, and I'm looking forward to talking to you. One quick comment and then a question. I think the G90D now is more accepted as a spectrum of diseases, not necessarily stationary. There is evidence for progressive, slow progressive degeneration. And my question is about the early receptor potential. You showed beautiful dark adaptation or recovery of the early receptor potential following a bleach. But my understanding was that you need a fairly bright light to actually elicit the early receptor potential. So how do you do basically one time point per retina, or how do you collect the whole curve?
Or can you speak to microphone, please?
Yes, I agree with that. First comment, the ERP takes a whopping amount of light. Basically, you hold a photo flash unit in front of yourself with a contact lens on, you flash it, you're bleached forever. So that's why I came up with this idea. Instead of looking at this normal recovery curve, model it by flashing and flashing and flashing until finally it hits an equilibrium. And we checked it. The numbers that come out of the classic recovery versus this declining asymptotic sleep, they're a little bit different. And one of the starting assumptions is from an old literature that says with a lot of light hitting a rod photoreceptor, hitting a rhodopsin, you put that rhodopsin, you can photoreverse it. You can bleach it and unbleach it and bleach it. And on average, with an intense flash of light, you bleach about 50% of the rhodopsin. So the idea of looking at an asymptotic decline takes advantage of the idea that you're not bleaching all of the rhodopsin.
Yeah, go ahead.
Yeah, and I agree with you. The G90D has a spectrum. And as I mentioned, in that family, there was a 63-year-old brother and a 64-year-old brother. 64-year-old had some peripheral pigmentation, and there was, I think, a 38-year-old who also had some. But the majority of them had nothing. So.
My follow-up on the early receptor potential, there's, of course, a lot of interest in human dark adaptation in the context of, biomarker for AMD and retinal degeneration. So is early receptor potential used? I'm not a clinician, but my understanding is not so much. And my question would be, if that's the case, and if so, why not?
After I did this work, there was very little work done in ERPs because of the concern for phototoxicity. So no, it is not used clinically. But fundus reflection densitometry, although a bit more laborious, is the way to do it. And I agree with you that AMD, age-related macular degeneration, quintessentially you lose your central vision when you're 73 years old or 65 or 92. So it's an age-related. preceding that, if you're really talking to a patient, you can elicit ideas that they're not seeing so well in dim light. There is an early rod component often to AMD.
Right, we have 3 more questions, 2 from the web, and Laura will finish because of time of late. So let's have those 2 questions.
All right, so Daniel, are you ready to ask your question?
Hi, Dan, how are you?
Can you hear me now?
Yes, Dan.
Oh, perfect. Okay. First of all, thank you very much, Paul, for this wonderful talk. It's a pleasure to see physicists speaking on ophthalmic issues. Very meticulous, very quantitative. I love it. My question is about ERP. As you know, now we can measure it with phase-sensitive OCT called optoretinography. And I was under impression that the rod signals in ERP will not be very visible electrically, but they're visible optically because discs are isolated. And the transition of rhodopsin isomerization into meta-2 is basically it's bound to the disc membrane, and all these discs are floating separately surrounded by the plasma membrane. So electrical signature is very small, if any. Unlike cones, where they're all embedded in a membrane and they all contribute, so the signature is very robust. But you have shown pretty strong R2, and I wonder how do you explain that?
I have no real cogent response to that, Dan. It's just an observation that is there. So yes, one would go back to the assumptions that are made that it shouldn't be there because it is. I don't have a better explanation for it. My understanding of the ERP is that it is pigment, a molecule of pigment in the membrane, within the membrane. When the molecule changes its shape, configuration, the charges on the molecule move in space, and that ultimately generates what we record as a voltage that propagates to the cornea.
Yeah, that's
So-
exactly right. It moves across the disc membrane, but each disc is isolated with an outer segment in rods, and so they should not contribute to electrically measurable signal outside the rod.
Well, they do, so
Yeah, exactly.
I can't tell you.
Exactly, that's exactly my question. Okay, thanks.
Let's talk next week.
All right, sounds good. Thank
Next
you.
question goes to Brent.
Hi, excellent talk. Great body of work. I had a question more specifically about the last few slides where you showed that 50% cone loss in the macula could be still at 20/20 vision. And also you showed that there was that remodeling with the cones moving more central or coming together and compacting. What do you think about ways to evaluate vision better? Do we need to do smaller spots instead of letter charts to be able to do early detection? And also, what do you think the role of any inner retinal remodeling is in improving vision or hiding that kind of cell death?
Two interesting questions. What is a metric for more precise measurement tracking photoreceptor demise and the consequence on vision? I think ultimately looking at them with AOCT phase shifted is going to get to a level of resolution beyond visual perception. One current measurement that is being emphasized, including in clinical trials with results going to the FDA for approval, is to use dim light and to measure visual acuity in dim light, called low luminance visual acuity. I don't yet understand the anatomic, physiologic basis for that. But I would think you take a photoreceptor, a healthy photoreceptor, it doesn't just die. Instead, it goes through a series of progressively shorter inner and outer segments. It's a metabolic failure of that photoreceptor. And consequently, when we use very bright eye charts, it saturates what's remaining. And so even a sick photoreceptor can respond, whereas with low luminance, there simply is not enough light. And you begin to sort out how many rods are actually functional under duress. So that may hold some promise. And I think that will be the near-term answer to your question. But longer term, I think it's going to be a phase detection OCT.
Great. Thank you so much.
All right, and final question goes to Caroline.
I think it was fantastic talk. So my question is about the STR portion of your talk. So could the STR measurement have some clinical relevance, perhaps to indicate eligibility of treatment? So I mean then in the sense that if you have this inner retina that is still the circuitry is still intact, could it indicate that these patients, of course assuming an optic nerve that's still intact, be eligible for perhaps like cell therapies or other like later stage therapies?
Thank you.
Thanks for that question. I don't have an answer. The question was, could the STR be useful in sorting out patients who would benefit from some kind of therapy? The difficulty, practical difficulty with the STR is you need to dark adapt a patient an hour. You need a patient who is very cooperative in terms of really actively participating in the measurement. And it takes a room where you have blocked out all remaining light. So just the criteria for recording the STR become difficult. I did, since I had that and I was measuring it, measuring the STR in patients, one of my early forays into X-linked retinoschisis was to look at the STR. And I found a significant impairment in producing the response. I don't really understand how that has advanced my understanding of XLRS, retinoschisis disease. So I don't have an answer to you as to whether it's useful, and then is it practically useful? Probably not. But it's fun.
Good. Thank you, Paul.
There's some coffee left.